Let me ask you something. When you picture Antarctica, how far back do you assume that picture goes? Most people, if they think about it at all, assume the answer is something like always. Antarctica is ice. It has always been ice. It sits at the bottom of the planet. It is cold. And cold places with ice tend to stay that way. It feels like one of the more stable facts about Earth. The kind of thing that does not need investigating any further. I want to be honest with you. I assumed the same thing until I started reading about what has actually been pulled out of the rock on that continent. Because sitting in a research collection right now, gathered from an island off the coast of West Antarctica, is a piece of fossilized wood. Not ice. Wood. The remains of an actual tree that grew in soil under open sky, on the same landmass that today sits buried under kilometers of solid ice and hosts some of the most hostile conditions for life anywhere on the planet. That single piece of wood forces you to ask a question most of us never think to ask. If trees were growing there, what did Antarctica actually look like before it became what we know today? And if it was not always frozen, what changed? Stay with me, because the answer involves continents drifting across an entire hemisphere, a switch in the planet's climate that happened faster than seems physically reasonable, and a wind that can make a grown, prepared, experienced person completely disappear within meters of shelter. Let us start with what is actually sitting in the ground down there. The fossil in question was recovered from West Antarctica, in a region where researchers have spent decades piecing together the deeper geological history of the continent. Wood like this does not form in the environment we associate with Antarctica today. Trees require liquid water, a growing season, soil that is not locked under permanent ice, and a climate mild enough to sustain root systems and photosynthesis across at least part of the year. None of those conditions exist on the Antarctic continent now, anywhere, at any time of year. Using geological dating techniques, researchers estimate the age of this fossil wood at roughly 130 million years old. 130 million years. Let me try to put that number somewhere you can actually hold on to it. That predates the asteroid impact that ended the age of the dinosaurs by around 65 million years, meaning this tree was alive and growing while dinosaurs still dominated the planet. Tens of millions of years before that extinction event ever happened. It predates the existence of most modern flowering plant families. It predates the Atlantic Ocean itself being anything close to its current width, since the continents were still in the middle of the long, slow process of separating from each other. And it was found on a continent now covered by an ice sheet that in places is over 4 kilometers thick, in a location where the modern climate would kill an unprepared human being in a matter of hours. Here is what I want you to sit with for a moment. This is not a single, isolated curiosity. Fossil wood is only one category of evidence, and researchers studying Antarctic geology have assembled a considerably broader picture from multiple independent sources. Leaf impressions, preserved with enough clarity to identify the shape and vein patterns of specific ancient plant species, have been recovered from several locations along the Antarctic Peninsula and offshore islands. Fossilized pollen grains, small enough to be carried and preserved in sediment layers, have been extracted from drill cores and used to reconstruct entire ancient plant communities layer by layer, essentially reading a botanical record directly out of the rock. Even amber fossilized tree resin has turned up in Antarctic sediment. The exact same substance that elsewhere in the world is famous for preserving insects from the age of dinosaurs in exquisite detail. Taken together, this is not evidence of a brief, unusual warm spell that produced 1 or 2 struggling trees clinging to survival at the edge of habitability. Multiple independent lines of evidence, fossil wood, leaf impressions, pollen records, and preserved resin all point toward the same conclusion. For a substantial stretch of its geological history, significant portions of this continent were not simply tolerable for plant life. They were green. It is worth understanding briefly how researchers actually arrive at a number like 130 million years, because the confidence behind that figure does not come from a single measurement, dating fossils. This old typically relies on examining the layers of rock surrounding the fossil itself, since the rock layers above and below can often be dated using radiometric methods that measure the decay of naturally occurring radioactive elements at known fixed rates. If a fossil is found sandwiched between two rock layers whose ages have both been independently measured, its own age can be constrained to fall somewhere within that range. Cross-referencing this with the known evolutionary history of the specific plant species identified in the fossil record, comparing them against similar specimens found and dated elsewhere in the world, allows researchers to narrow the estimate further still. This is why a figure like 130 million years is treated as a genuinely reliable scientific estimate rather than a rough guess, built from multiple independent, cross-checked lines of physical evidence rather than any single test. So, how does a landmass that hosts actual forests end up as the coldest, driest, most consistently frozen place on Earth? The answer is not really about Antarctica's climate changing in place. It is about Antarctica itself moving. Here is something that took me a while to fully internalize, even though I understood the basic concept of plate tectonics well before I looked closely into this. The continents are not fixed. They ride on plates of solid rock floating, in an extremely slow, extremely gradual sense, on the semi-molten layer of the Earth's mantle beneath them. Over the span of tens of millions of years, entire landmasses drift, collide, split apart, and rotate into completely different positions on the globe. Antarctica was once part of a much larger supercontinent that geologists call Gondwana, which also included what is now South America, Africa, India, Madagascar, and Australia, all fused together into a single enormous landmass that dominated the southern hemisphere for hundreds of millions of years. And critically, during large portions of Gondwana's history, the piece of that supercontinent that would eventually become Antarctica was not sitting at the South Pole at all. It was located at significantly lower latitudes, in some periods within a range that would today correspond to temperate or even subtropical climate zones, similar to conditions you might associate with parts of modern-day New Zealand or southern Chile. At those latitudes, with that climate, forests could grow. The fossil wood we started with is a direct physical remnant of exactly that period, a tree that lived its entire life in conditions that had nothing in common with the Antarctica we know today, on a piece of crust that, over an almost incomprehensibly long span of time, was still slowly making its way toward the bottom of the planet. Gondwana began breaking apart roughly 180 million years ago, splitting gradually into the separate continents we recognize now. The process did not happen all at once, or in a single clean fracture. Different sections of the supercontinent separated at different times, along different rift lines, over an enormous span of geological history. South America and Africa were among the earlier pieces to separate, pulling apart to eventually form the South Atlantic Ocean between them. India broke away and began an extraordinarily long journey northward that would eventually see it collide with Asia and push up the Himalayas. Australia remained attached to Antarctica for longer than most of the other fragments, the two landmasses staying connected well after other sections of Gondwana had already gone their separate ways. Antarctica's own position shifted southward across tens of millions of years, a process so slow that within any single human lifetime, or even across the entire span of recorded human history, the movement would be completely undetectable without precise satellite instrumentation capable of measuring centimeters of movement per year. And yet, added up across geological time, that same slow drift was enough to carry an entire continent, forests and all, from a temperate zone into the polar region it now occupies. It is worth pausing on what that forest actually looked like, because it is easy to picture something generic and miss how specific the picture researchers have actually reconstructed really is. This was not a landscape of palm trees or anything resembling a tropical jungle. The Antarctica of that era, even at its warmest, still experienced months of extended winter darkness at those latitudes. The same basic axial tilt that governs polar seasons today already existed then. What grew there instead were conifers, related to trees still found in South America and parts of Australia today, along with early flowering plants and ferns, adapted specifically to a climate with mild, wet conditions for much of the year, interrupted by a genuine months-long polar night during winter. That detail matters because it means these were not simply displaced tropical species clinging to survival at the edge of their range. These were plants specifically adapted to seasonal darkness combined with a relatively mild temperature range, an ecological niche that does not have a clean modern equivalent anywhere easily accessible today. Understanding how photosynthesis, growth cycles, and root systems functioned under months of continuous winter darkness, followed by months of continuous summer daylight, is itself an active area of paleobotanical research, and one with a strange modern relevance, since it offers scientists a working model for how plant life might theoretically function on planets or moons with similarly extreme seasonal light cycles. Are you still with me? Because I know continental drift on its own is the kind of fact that people nod along to without it really landing. Stay with me, because the next part is where this story stops being simply strange and starts being genuinely alarming in the sense of how fast major climate transitions can actually happen once the right conditions line up. Because here is the thing that surprised me the most in researching this. Antarctica did not freeze gradually in some slow, centuries-long cooling that mirrored its southward drift. The transition into a fully ice-covered continent happened, geologically speaking, remarkably fast, and it happened for reasons that had almost nothing to do with the continent's position alone. Around 34 million years ago, at a boundary geologists call the Eocene-Oligocene transition, Antarctica went from a landmass that still hosted at least some vegetation and a considerably milder climate, to a continent developing a substantial, largely permanent ice sheet in a window of time that, relative to the previous tens of millions of years of gradual drift, looks almost sudden. Two major factors appear to have converged at that point. The first involves ocean circulation, and specifically a body of water called the Drake Passage, the stretch of ocean separating the southern tip of South America from the Antarctic Peninsula. Earlier in Antarctica's history, when it was still connected to South America and Australia through the larger Gondwana landmass, ocean currents flowing toward the pole were disrupted by that connected land, forced to divert north before they ever reached the continent directly, carrying warmer water from lower latitudes close enough to Antarctica's coastline to keep the climate there considerably milder than it is today. As Gondwana finished breaking apart and the Drake Passage fully opened, somewhere in the range of 30 to 40 million years ago, depending on which specific geological evidence researchers weight most heavily, deep cold water was, for the first time, able to flow in a complete, unbroken loop entirely around Antarctica. Uninterrupted by any landmass at all, This is not a small technical detail. Before that gap opened, no continuous circumpolar current could exist, because land was physically in the way. Once the passage opened wide enough and deep enough, the geometry of the entire Southern Ocean changed. This created what is now called the Antarctic Circumpolar Current, still the largest ocean current system on the planet by volume of water transported, moving more water than any other current on Earth, more than the Gulf Stream, more than any tropical current system, simply because it is the only current able to flow uninterrupted in a complete circle around an entire continent without ever being blocked by land. And its effect on Antarctica was profound. By circulating cold water in a continuous ring around the continent, it effectively insulated Antarctica from the warmer currents that had previously reached it from lower latitudes, cutting the continent off thermally from the rest of the global ocean system in a way that had never existed before. Think of it as a moat, except the moat itself is the mechanism actively refrigerating everything inside it, continuously, permanently, for as long as the current keeps flowing in its closed loop. The second major factor was a substantial decline in atmospheric carbon dioxide levels during roughly the same geological window, driven by long-term changes in volcanic activity and rock weathering processes operating over millions of years. Volcanic activity releases carbon dioxide into the atmosphere, while the chemical weathering of certain rock types, particularly silicate minerals exposed by mountain building and erosion, gradually pulls carbon dioxide back out of the atmosphere and locks it into new mineral compounds over long time scales. Across the tens of millions of years leading up to this transition, the balance between those two processes shifted, with weathering outpacing volcanic output, resulting in a gradual, long-term decline in atmospheric carbon dioxide concentration. Lower atmospheric carbon dioxide meant less heat retained near the planet's surface, compounding the cooling effect the newly formed circumpolar current had already begun. Climate scientists studying this period have identified something that functions almost like a dial with a specific tipping point built into it. Below a certain concentration of atmospheric carbon dioxide, once combined with the newly isolating effect of the circumpolar current, permanent ice sheet growth on Antarctica became not just possible, but essentially inevitable, a self-reinforcing process. Once ice begins to accumulate, its bright white surface reflects a significant portion of incoming sunlight straight back into space rather than absorbing it as darker rock or vegetation would, which cools the surface further, which allows more ice to persist through the following summer instead of melting, which increases the reflective surface even more the year after that. This feedback loop, once triggered, tends to accelerate itself rather than stabilize, at least until it reaches a new equilibrium. Put those two factors together, a continent recently isolated by a complete ring of cold ocean current, combined with declining global carbon dioxide levels crossing this reflective feedback threshold, and you get conditions that, once crossed, appear to have triggered a relatively rapid buildup of permanent ice across the continent, geologically speaking, occurring over a span that current research estimates at somewhere in the range of a few 100,000 years, rather than the tens of millions of years the drift itself had taken. A few 100,000 years sounds enormous in ordinary terms, but set against the timescale of the continental drift that came before it, tens of millions of years, this was closer to a threshold being crossed than a gradual slide. Once ocean circulation and atmospheric chemistry lined up in the right way, Antarctica's transformation from a partially vegetated continent into the ice sheet we know today happened in what amounts to a geological blink. Here's what I keep turning over in my head about this. We tend to think of planetary climate as something that shifts slowly, predictably, giving ecosystems time to adapt or relocate. Antarctica's own history suggests that once specific thresholds are crossed, whether in ocean circulation patterns or atmospheric composition, the resulting transformation can happen far faster than the slow processes that set it in motion. The forests did not fade out gracefully over tens of millions of years, matching the continent's drift south. They existed, and then, within a window that is short by comparison, the conditions that allowed them to exist were gone. There is also a broader consequence to this transition that goes well beyond Antarctica's own coastline, one that connects this single continent's history to the shape of ocean ecosystems everywhere. The formation of the Antarctic circumpolar current did not just refrigerate one landmass, it fundamentally reorganized how nutrients circulate through the entire global ocean. Cold, nutrient-rich water drawn up from the deep ocean along the edges of that circumpolar system feeds some of the most productive marine ecosystems on the planet even today, supporting enormous populations of krill, which in turn support whales, seals, penguins, and seabirds across the entire Southern Ocean. In a very real sense, the same geological event that froze the forests off this continent also built the engine that still powers one of the richest food webs anywhere in the ocean. A direct, unbroken line running from a shift in plate tectonics roughly 34 million years ago to the abundance of marine life in the Southern Ocean today. Let me bring this back to something closer to the present, because the story of how Antarctica became frozen is not the end of what makes this continent strange. It also happens to be, right now, the driest and windiest place on the surface of the Earth. And understanding why connects directly back to everything we have just covered. Despite holding roughly 70% of the planet's fresh water locked into that enormous ice sheet, the interior of Antarctica receives so little annual snowfall that large portions of it technically qualify as desert. Some of the driest land environments found anywhere on the planet, drier than the Sahara in terms of annual precipitation. This sounds like a contradiction until you understand the mechanism behind it. A desert, by the definition that actually matters scientifically, is not defined by heat or sand. It is defined by how little precipitation falls each year. By that measure, the high interior plateau of Antarctica receives less annual snowfall, converted to water equivalent, than most of the Sahara receives in rainfall. The same atmospheric and oceanic isolation that allowed the ice sheet to form in the first place also cuts the continent off from the moisture-bearing weather systems that bring regular precipitation to almost everywhere else on Earth. The ice sheet itself is less the product of heavy annual snowfall and more the product of an almost unimaginably long accumulation, tiny amounts of snow falling year after year for hundreds of thousands of years, compressing under their own weight into something that behaves less like snow and more like solid ancient glass. And then there is the wind. Cold, dense air forms constantly over the elevated interior of the ice sheet. And because Antarctica's interior sits at a genuinely significant elevation, the ice itself piling up over kilometers of thickness, that dense air accelerates as it flows downhill toward the coast, funneled and channeled by the shape of the terrain beneath it, gaining speed the way water gains speed running down a steep, narrow channel rather than spreading out across flat ground. These are called katabatic winds, and along parts of the Antarctic coastline, they are recorded reaching speeds close to 300 kilometers per hour, among the fastest sustained surface winds ever measured anywhere on the planet. 300 kilometers per hour is faster than the sustained wind speed of a Category 5 hurricane, the highest classification used anywhere in the world for tropical storm systems. It exists here not as a rare, singular, extreme weather event arriving once in a season before dissipating, the way a hurricane is treated almost everywhere else on the planet, but as a recurring, semi-predictable feature of the local climate, something researchers stationed there plan their entire daily routines around, checking wind forecasts the way people elsewhere check for rain. 300 kilometers per hour is faster than the sustained wind speed of a Category 5 hurricane. It exists here not as a rare, singular extreme weather event, the way a hurricane is treated everywhere else in the world, but as a recurring, expected feature of the local climate, something researchers stationed there have to plan their entire daily routines around. These winds are strong enough that certain research stations impose strict rules about when personnel are permitted to travel even short distances outdoors, sometimes as little as a single kilometer between buildings connected by nothing more than open, exposed ground. In extreme conditions, a phenomenon called whiteout can occur, where blowing snow combines with flat, diffuse light, often under an overcast sky with no clear sun position to orient by, to erase all visible depth and horizon entirely. Every visual reference point disappears at once. The line between ground and sky simply stops existing. A person can become completely disoriented, losing all sense of up, down, or direction within meters of a doorway they have walked through 100 times before, in conditions where even careful counting of steps can fail to bring someone home if the wind shifts their path without them realizing it. There are documented cases of researchers becoming lost and never being found again within extremely short distances of shelter, victims not of falling or extreme cold alone, but of simply losing all spatial orientation in conditions where the ground and the sky become visually indistinguishable from each other. Search parties, in some of these cases, have covered the exact ground where a person must logically have been standing, without ever locating them, because in true whiteout conditions, visibility can drop to a few meters or less, and a person lying just outside that radius is, for practical purposes, invisible. I think about that specific detail more than almost anything else in this story. A continent that once grew forests warm enough to support root systems and photosynthesis now produces wind conditions capable of erasing a person's sense of direction within the length of a city block. The same landmass, a completely different world. So, where does this leave us when we try to hold the whole story in our heads at once? A tree grew roughly 130 million years ago in conditions mild enough to support it, on a piece of crust that would eventually become part of a supercontinent breaking slowly apart. Over the following tens of millions of years, that piece of crust drifted south, carried by forces operating on a time scale so vast that no single human observation could ever have detected the motion directly. And then, roughly 34 million years ago, once an ocean current finally closed into a complete ring around the newly isolated continent and atmospheric carbon dioxide dropped below a critical threshold, the transformation from a still partially vegetated landmass into a fully ice-covered continent happened in a window that, by comparison to everything that came before it, looks almost sudden. We were wrong about Antarctica always being frozen, in the most literal sense possible. It was not frozen for the majority of its geological history. It became frozen at a specific and identifiable point in time, for specific and identifiable reasons, and the process of it happening took a fraction of the time it took for the continent to simply arrive at its current position on the globe. I think what unsettles me most about this is not really the forests, remarkable as it is to imagine trees growing on ground that is now buried under kilometers of ice. It is the speed of the transition once the right conditions aligned. We tend to assume that planetary scale change requires planetary scale time. Antarctica's history suggests otherwise. Slow, almost undetectable drift over tens of millions of years, followed by a threshold, crossed within what is, by comparison, an almost immediate window, after which the entire character of a continent was permanently rewritten. There is a particular kind of vertigo that comes from holding both timescales in your head at once. Tens of millions of years for the drift itself, a span so long that entire mountain ranges rose and eroded away to nothing within it. Entire species evolved and went extinct several times over. And then, within a window that is a tiny fraction of that first number, the whole outcome flipped permanently from a green continent to a white one. Nothing about the pace of the earlier process would have predicted the pace of the second one. If you had been watching Antarctica drift south across those tens of millions of years, extrapolating forward from everything you had observed up to that point, nothing in that slow, gradual pattern would have prepared you for how quickly the actual freeze, once triggered, arrived. That fossil wood is still sitting in a research collection somewhere, a physical object you could hold in your hand, evidence that the coldest, driest, most hostile large landmass on the planet was once green enough to grow trees. It did not stay that way because ice is somehow the natural, permanent state of a pole. It stayed that way because a specific combination of ocean current and atmospheric chemistry locked it into place, roughly 34 million years ago, and nothing since has been strong enough to reverse it. Nothing, that is, until recently. I think it is worth sitting with one final piece of this because it connects the deep past directly to right now. The same two forces that froze this continent, ocean circulation patterns and atmospheric carbon dioxide levels, are the same two variables climate scientists watch most closely today when studying modern Antarctic ice loss. Atmospheric carbon dioxide, after remaining relatively stable for a very long stretch of human history, has risen sharply over the past 2 centuries, moving back in the opposite direction from the multi-million-year decline that helped freeze this continent in the first place. Researchers monitoring the Antarctic circumpolar current have also documented changes in its temperature and behavior in recent decades. The same system that once locked in the freeze now showing measurable signs of warming at certain depths. I want to be careful here, because the geological transition that froze Antarctica took a few 100,000 years, even in its relatively fast version, and nothing currently observed suggests a return to green forests is remotely close, or even in the same category of event. But the underlying mechanism is the same one this entire story has been about. This is not a continent whose ice is guaranteed by its location alone. It is a continent whose ice exists because of a specific measurable combination of ocean current and atmospheric chemistry, the same two variables that are shifting again, this time in the opposite direction, on a time scale measured in decades rather than millions of years. The surface is not the whole story. It never was. If this documentary gave you something you did not have before you pressed play, if Antarctica feels like a genuinely different place to you now than it did 20 minutes ago, then subscribe to Abyss Files. Every week we go somewhere the surface does not show you. Every week there is something the ocean, or in this case the ice and the ground beneath it, is still hiding. And I promise you, it only gets stranger from here.
Imagine a thick green rainforest, towering trees, dense ferns, swampy ground, and not a single glacier in sight. Now here's the twist. This rainforest did not exist in the tropics. It existed in Antarctica. The coldest, most hostile continent on Earth today was once warm, wet, and very much alive. Scientists now say that around 90 million years ago, during the age of dinosaurs, Antarctica sat under a temperate rainforest less than 1,000 kilometers from the South Pole. A major scientific study analyzed fossil soil, roots, pollen, and spores extracted from deep beneath the seafloor near West Antarctica. What they found was staggering. The soil layers were once part of a living forest floor. Fossilized roots show a dense web of vegetation. Pollen and spores point to conifers, ferns, and even flowering plants. In short, this was not a barren landscape. This was a complex, thriving ecosystem. Scientists estimate that the average annual temperature near the South Pole was around 12 degrees Celsius. Summer temperatures may have climbed to 19 or even 20 degrees, similar to what we see today in part of Wales. And all of this happened during long polar nights, months of darkness each year, when the sun barely rose above the horizon. So the question is, what made that possible? And the answer lies in Earth's ancient atmosphere. The period is known as the Cretaceous greenhouse, the warmest climate phase the planet has seen in the last 140 million years. Carbon dioxide levels were far higher than today. There were no massive ice sheets. Heat was trapped more effectively in the atmosphere, and the result was even the poles were warm enough for forests to flourish. Modern Antarctica is locked under kilometers of ice. Temperatures plunge far below freezing, and carbon dioxide levels, while rising rapidly, are still very much lower than they were back then.